Okay, so the next video here is a very common method to collect gas. But when we collect gas, uh, we need to take into account what we're collecting it over. So one of the ways that we collect gas is while we fill up a tube with water or a container with water, and that means that, okay, it's all filled with water, and we can bubble in the gas to displace the water, and thus the only thing that's trapped is the gas that we were going for. Now, the one thing that we have to consider is when we use water to do that, water evaporates, right? So some of the water uh, actually goes from the liquid phase to the gas phase, and depending on the temperature, there's more moles of water that could potentially be in the gas phase. And remember, with Dalton's law of partial pressures, the total pressure uh, involves the partial pressure of each individual gas in the container. So in that case, we would have the gas that we collected, but also the water vapor and its pressure that it contributes. So very common to collect gas by water displacement. Okay, so ultimately, we need to take into account the total pressure and the partial pressure of the water, okay, into this. Now, these values we look up in the chart, okay, for water vapor, because they're all temperature dependent. Higher the temperature, the more water vapor there will be, okay. So, for an example of this is the little image up above here. Okay, we got a sample of solid potassium chlorate, and it's heated in a test tube. We have the reaction there. The oxygen produced is collected by water displacement at 22 degrees Celsius. And total pressure of 754 torr. The volume of gas collected is 0.65 liters, and the vapor pressure of the water is 22. Vapor pressure of water at 22 degrees Celsius is 21 torr. Okay, and they want us to calculate the partial pressure of O2 and gas collected. Uh, the gas collected, and then ultimately the mass of the CO3 in the sample. So a little bit of stoic at the end of this. Okay. So first thing we need to do is we got to figure out the partial pressure of oxygen that's in there. Okay. So let's do that. So we know the pressure total minus the pressure of H2O is going to be equal to the pressure of oxygen in the air. So we know that the pressure is 754 minus the partial pressure of 21 it's going to be equal to the pressure of O2. So that means the pressure of the oxygen gas is equal to 733 so now that we know that, we can actually use the ideal gas law. You'll notice that the ideal gas law is something that we use a ton. We need to know how many moles, right? Moles of O2 this is. All right, and we can use the ideal gas law to do that because we need to know moles. Because once we know moles, hey, then we know moles of that, which ultimately we can get grams because they want to know the mass of the sample we started with. All right, so pressure here is equal to 733. For the volume was 0.65 milliliters. The moles of gas, we don't know. That's what we're trying to solve for. Okay, the R value here in this case is 62.36. Remember, that's on the back of your yellow periodic table. And the temperature is 22 degrees Celsius. So 22 plus 273 is 295 K. We always want to operate in kelvins. So if we do the algebra there, solve for our moles of O2, we end up with 0.0259 moles of O2. Okay? All right, so since we know moles of O2, 0.0259 moles, we do a little stoichiometry here. We got to do our sorority moles, we do our mole ratio, 2 moles of KClO3 for every 2 moles of, or I'm sorry, 3 moles of O2. And then we multiply by the mole mass. So in 1 mole of potassium chlorate, we have 122.55 grams. So ultimately, when we do that math, we end up with 2.12 grams of potassium chlorate. Okay, and those answers match. There we go. Okay. So that's one thing that we can do. Another example of this would be the next question here. We got an apparatus. We got 5 liter flask containing nitrogen at 25 degrees Celsius. You get 831 kilopascals, joined by a valve. So if I draw this, so we got flasks joined by this valve. So on one side we have 5 liters, and it's 831 kPa. And that's nitrogen gas. Okay. And on the other side, it's 8 liters, and it's of argon, and it's at 1.7 kPa. And ultimately, they open the valve, and the gases mix. And they want to know what the partial pressure of nitrogen is, partial pressure of argon after mixing, and what the total pressure is. Okay. Well, since we know moles, right? Because we got to know the mole fraction of our gases in order to figure out what the partial pressure of each one is after we're done mixing them. So we need to do an ideal gas law for N2. We need to do an ideal gas law for argon. And then we need to do for both containers. Okay, so we're going to do PV equals nRT for each of these situations because we need to figure out how many moles of nitrogen and how many moles of argon there are. Okay, so in this case, we have 831 kPa at 5 liters is equal to N times kPa. The R value is 8.314. Temperature is 25 plus 290 plus 273, so that's 298. So we know there are 1.68 moles of nitrogen gas. We do the same thing here for argon. 1.7. Volume is 8 liters. That's equal to N times 8.314 times 298. So moles of gas equal 0.138 moles of argon. Okay, so that's great. So our total moles are equal to 1.815 moles of gas. All right, so that's great. Now, what we need to know now is the total pressure, and that's why we have to do both together after mixing in order to find the pressure total. Right, so we found the moles of each gas. Now when we mix them together, well, we got to find what the total pressure is between the whole thing. Now that we've made it 14 liters. All right, so our pressure total times our volume is going to be equal to our moles total times R times T. All right, so our pressure total. For our variables, we have a 13 liter flask. Our moles total are 1.815 times our R value, which is 8.314, times our temperature, which is 298. So our pressure total is equal to 346 kPa. So we got our total pressure, and once we know our total pressure, we can use the mole fraction to find the partial pressure of each individual gas. So pressure of the 2 is equal to the mole fraction times the total pressure. So 1.68 divided by 1.815 times 346. So we end up with 340 kPa. And the pressure for argon is equal to mole fraction 2.135 divided by 1.815 times the total pressure, which is 346. And added up with 25.7 kPa. That's all the boxes. We're all set. So that is a couple of examples of measuring pressure over water displacement. And the collected gas over water, you've got to take into account the vapor pressure, the partial pressure that's due to the vapor pressure of water. Okay, one more video to go.